Hi, and welcome to Math 232, Linear Algebra. This is section 6.2, diagonalization. So we're going to get a bunch of practice here also computing eigenvalues and eigenvectors. So it'll be a nice review of section 6.1 as well. So the idea here is that we're going to want to figure out if we can take a matrix and compute something from it. So but the idea is we're going to be given a matrix A, and then what we want to know is, can we do this and where this results in a diagonal matrix? So can we find a matrix P, so such that P to the minus 1 A P will equal D when D and D will be diagonal? That is our goal here. We just define the word trace as being the sum of the diagonal elements. Okay, so we'll proceed at first to say what it means when two matrices are similar. Two matrices are similar if you can find a matrix P such that you can establish this relationship between A and B. If there's a matrix P such that P to the minus 1 AP is equal to B, then A and B are said to be similar. So the first thing we're going to do is we're going to be given this matrix P, and we're going to show that A and B are similar. So you get a sense of what it means for the matrices to be similar. So the first thing I need to do is calculate the inverse of P. So I'm simply going to write that out. So you could, I want you to do this, recall 2 by 2 inverse formula. So recall that formula, compute the inverse, make sure it's this. I computed the inverse and got this. So step one, I'm computing the inverse of P. Now I'm going to see what happens if I take P to the minus 1, the inverse of P, multiply that by A, and then multiply that again by P. So I'll put it here, P to the minus 1, the inverse of P. Then next I will multiply by A. And then I will multiply that by P. Okay, so I'm going to proceed to do this matrix multiplication. I'll do a couple of these by hand, but for this one, why don't you stop the video, do this matrix multiplication, and then confirm that it comes out to this. So there we have this matrix here is B. The result is B. This guy right here is B, and this guy right here is A. And so we have found a matrix P that if we go P inverse times A times P, we get a matrix B. And then I'm going to say that A and B are similar. So let's take a look at some of the attributes that A and B share. Now that we've established, because we could find P, we've established that A and B are similar. Let's say some things about A and B. Okay, let's take a look at the determinant. So I'm claiming here that both A and B have the same determinant. So let's just calculate that. The determinant of A is minus 12 times 13 minus 15 times minus 10. And that comes out to be minus 6. And then the determinant of B is computed as minus 12 times 13 minus 5 times minus 30, and that is also minus 6. So A and B have the same determinant. That always happens. Okay, I claim also that A and B, being similar matrices, have the same eigenvalues. They have the same eigenvalues. So let us calculate what those are. So how do I calculate an eigenvalue? I take the determinant of lambda I minus A, and I set that equal to 0. So let me take that determinant. That is going to be lambda plus 12 minus, this is lambda I minus A, like that. Okay, and then I do A times D minus B times C. I'm going to have to do a little bit of algebra there, expand and combine like terms, and I get here I get this polynomial. I factor that polynomial, and I get that guy there. Okay, so the matrix A has two eigenvalues. Lambda 1 is going to be 3, and lambda 2 is minus 2. Okay, so there's two of them. I will then now compute the determinant of lambda I minus b. And that will get me this guy here. This will be lambda plus 12 again. This will be minus 5. This will be 30. And then this guy here down here will be lambda minus 13. Okay, so now I'm computing the eigenvalues of b. I get a characteristic polynomial of x plus 12 multiplied by x minus 13 plus 150. And I see that right at this point, I can actually see that it's the same as this guy up here. 5 times 30 is the same as 15 times 10. So I get the same. So I find out that lambda 1, lambda 2 are the same, 3 and minus 2. So the eigenvalues are the same. I also claim that the rank of A is equal to the rank of B. So how would I find the rank? Well, I would simply take matrix A and row reduce. So I have 12, 15, minus 10, 13. So I row reduce like that, and that row reduces to the identity matrix. It's got a rank of 2. A has a rank of 2. I take B, I row reduce. I row reduce, and I also get the identity matrix. That means that B has a rank of 2. So the rank of A is the same as the rank of B. The same trace. So the trace is the sum of the diagonal elements. So the trace of A, which is the sum of the diagonal elements, is going to be 1 minus 12 plus 13. And since the diagonal elements are the same, in fact, in this case, this is not always the case, but the diagonal elements are the same in this example. So the trace of A, and this is also the trace of B. Okay, one thing I do want to point out, the eigenvalues of A and B are the same, but the eigenvectors are not. So I'm going to sort of highlight that and say when two matrices are similar, they have the same eigenvalues, but they don't necessarily have the same eigenvectors. Okay, so, but not the same eigenvectors. Okay, so I did the calculations here. What I suggest you do is make these calculations yourself. Right, you can stop the video, calculate the eigenvectors for A, calculate the eigenvectors for B, turn the video back on and see and check your answer. So I did this. I calculated the eigenvectors for A, and for lambda is equal to 3, I got the eigenvector. So let me call that lambda 1. I got the eigenvector V1 1 1. And then for the eigenvalue lambda 2 is minus 2, I got the eigenvector B2, which is 3/2 and 1. And I did the same thing for matrix B. Get lots of practice this way. So for matrix B, I also computed the eigenvectors for these eigenvalues, and I got for lambda 1, let's see, which one did I call lambda 1? I called lambda 1 in this case minus 2, and I got the eigenvector V1 to be 1/2 1, and I got for the other eigenvector, which corresponds to eigenvalue of 3, I got this eigenvector here. Okay, they're not the same. So the eigenvalues are the same for similar matrices, but here you can see the eigenvectors are different. So that is what it means for two matrices to be similar. Okay, so now we're going to move from that basically to say if that matrix, that second matrix on the right-hand side by himself, this guy here, is diagonal, then A is diagonalizable and P diagonalizes A to its diagonal form D. Okay, so we're going to do an example here. We want to show that this matrix P diagonalizes A, and we want to find what does it diagonalize to. So let's, we've been given P. We don't yet know how to find P. Don't worry if you're thinking, where does this mystery P comes from? We don't know yet. So that's coming in our tail. Okay, so let's compute the inverse of P. That is going to be 1 over the determinant. That's 6 plus 1 multiplied by let's see here, 3. I'm going to change my example. I think my notes didn't properly update here, so I'm going to change my example right here. So I'm just going to change these. I had changed these, and there somehow my thing is not correct here. So let me just fix that problem. Problem's going to stay the same, but I'm going to change the numbers. Let's call P that, and let's call A this guy here. I changed the example since the time I printed these notes. Sorry about that. Okay, let's try that. 11, 6, 9 minus 4. Okay, so I'm going to take the inverse of this matrix right here. There, that's better. Okay, and that comes out to this here. So I'm going to then multiply this P to the minus 1 A P, and then there's going to be that product. That's going to be 3/7 or 1/7 minus 1/7 and 2/7. And I'm going to multiply that by A. And then I'm going to multiply that by P. And I make that product, stop and check me, and I get this guy here. And you'll notice that this is a diagonal matrix. It's a diagonal matrix. This is the matrix D, and it is diagonal. So the matrix A is similar to the matrix D, and the matrix that is similar to is a diagonal matrix. I'm going to foreshadow the exciting things that are coming. Let's just take another look at this matrix A. There it is. I'm going to compute the eigenvalues of A. So I will go to take the determinant of lambda I minus A. That'll be the determinant of lambda minus 11, minus 6, minus 9, lambda plus 4. And that's going to be 4 minus 54. I have that then becomes lambda squared minus 7 lambda minus 98. And that is lambda minus 14 and lambda plus 7. Okay, so we see that the eigenvalues of A are lambda 1 is equal to 14 and lambda 2 is equal to minus 7. Those numbers should look highly familiar. They're right here. Okay, so those two numbers are the eigenvalues of A. Oh, so something is up here, and so what else can I say here? How about you do this? You compute the eigenvectors of A, and see where they are. Like, are they a part of P? Are they a part of P to the minus 1? Are they rows? Are they columns? So if you compute those eigenvectors, you'll see something kind of interesting there. Okay, so there are some conditions that a matrix must meet in order to be diagonalizable, and they are listed here. A matrix is diagonalizable if and only if there exists a basis for Rn. That means there has to be n eigenvectors of the matrix. It's diagonalizable if and only if every eigenvalue has its geometric multiplicity equal to its algebraic multiplicity. And then it's also diagonalizable, but only if it has n distinct eigenvalues. So the way to be careful about this is if you compute that there is n distinct eigenvalues, then you know it's diagonalizable. If you compute and you only find out you have, but it doesn't matter, n minus 2 distinct eigenvalues, then you get no information. You have to say, okay, I have to check one of the other two conditions. So be careful, that's not quite the same statement. One of them is if, and the other two are if and only if. So this one is usually easiest. But note if versus if and only if. Awesome. Okay, so here's a question then. Determine if these matrices are diagonalizable. And so I'm going to check what the eigenvalues are. So I'm going to check the eigenvalues of A, determinant of lambda I minus A. And I'm going to do the same thing for matrix B. I'm going to check the eigenvalues of each one of them to try to figure out if these things are diagonalizable or not. Okay, why don't you stop the video and do this yourself? These are just good. This is good practice. That will be then the determinant of lambda minus 4 minus 4 minus 4 lambda minus 4. That, and that is going to be lambda minus 4 squared minus 16. And that is going to be lambda squared minus 8 lambda, and that's lambda times lambda minus 8. So we have for matrix A, we have two eigenvalues, 0 and 8. There they are. So we have two distinct eigenvalues, and it's a 2 by 2 matrix. Therefore, A is diagonalizable. Okay, now, how did we know this was going to happen? In fact, I'm going to point something out here. This, we should, in some sense, just by looking right here, I could tell you that. Why? Because I look at matrix A and I'm like, hey, the determinant's obviously 0. I mean, that's 4 by 4 minus 4, 4 times 4 minus 4 times 4. So I can look at A and I can see that the determinant of A is 0. I know that A is not invertible. And in 6.1, we realize that that is equivalent to saying that lambda equals 0 is a eigenvalue. Okay. A is still diagonalizable. Okay, I can go through with B and I get this guy here. I get the minus 3, 0, 3, lambda minus 3. So I compute lambda I minus B. I get this. I take the determinant. I get this, lambda minus 3 squared. I find out that lambda equals 3 is an eigenvalue. And it has algebraic multiplicity equal to 2. Okay, so I see that it only has one distinct eigenvalue, but I don't assume that it's not diagonalizable yet, because this does not go the other way. This doesn't say, right, okay, I went through that. So we have to be cautious. So now what I'm going to do is I'm going to find the eigenvector associated here. So I'm going to solve put the eigenvalue equal to 3, and I get this matrix here like that, and I'm going to be solving that for AX equals 0. I row reduce, I get this, and that with the 0 still there, and I find then that the corresponding eigenvector is T times, let's see what's happening here. The first component is 0 and the second component is a free. So it's T. So what is the, this is a one-dimensional basis. And so I have that the geometric multiplicity is equal to 1. And I see that the algebraic multiplicity not equal to the geometric multiplicity, I will not be able to diagonalize matrix B. How do we find this mystery P so that we can diagonalize these things? So it's this statement right here. That's all we're going to be doing. Now, this is it really for this lecture. What is a diagonalization, and how do you figure out what the appropriate matrices are? And this is the key statement right here. That matrix P, which diagonalizes A, consists of the eigenvectors of A as columns. So this guy right here was in our previous example. So let us remember for A. So I'm going to do A first. I have that lambda I minus A is this guy here. Lambda minus 4, 4, minus 4, minus 4, and lambda minus 4. And I will write out the eigenvalues here. They were these two guys here. This is for A. We already did this. Okay, now I'm going to find the eigenvectors. So I'm going to take this, I'm going to put lambda equal to 0, and then I'll have this here. And that's easily row reduced down to 1, 1, 0, 0. You may notice that I'm just leaving off that 0, 0. I mean, nothing happens to these 0, 0s. They could be here if you want. But after a while, I don't need to see those there. You can put them in. It's not wrong. I am solving AX equals 0. Okay, that gives me an eigenvector here, V1 of minus 1, 1. Then I'm going to do the same thing for the, so this one was that one. And now I'm going to do the same thing here for the eigenvalue of 8. I'm going to take 8 minus 4 and get 4. And then I have minus 4 and minus 4, and then 8 minus 4, and I'll get 4 again. Then I'm going to take that and row reduce, and I get this guy here, 1, minus 1, 0, 0. And I get the eigenvector associated with the eigenvalue of 8. I get the eigenvector 1, 1. So now I've got two eigenvectors. Now, what I'm saying from this highlighted statement, the highly important statement here, I now know what P is. P is the eigenvectors of A put in as columns. Doesn't matter which one you put in first. Okay, so P could be that, and I could also put this guy as the first column, this guy as the second column. Does not make any difference. I mean, it looks slightly different, but you'll still get a diagonal matrix. So I get P. Then I'm back in fact now when I gave you P from before. Now you know how to find P yourself. Now we can calculate the inverse of P. That is going to be 1 over minus 1 minus 1 multiplied by 1 minus 1 minus 1 minus 1. And that gives me this matrix here, P. Like that. And then I see P to the minus 1, A, P is going to be P to the minus 1. That is this. A, P. I multiply all those things together, and why don't I in fact do this a little bit more longhand? I've just been doing this a bit quicker. So I leave the first matrix. I'm going to multiply these two guys, and I'm going to get this thing here, 0, 8, 0, 8. And then I can do the multiplication of these two, and I get 0, 0, 0, 8. It's a diagonal matrix. There's only non-zero entries on the diagonal. It's a diagonal matrix. And further, let's check this out. This entry and this entry are the eigenvalues. So we found P such that when we multiply like this, we get a diagonal matrix, and the entries on the diagonal are the eigenvalues. Okay, that was A. We're gonna have to, let's just put a hold on this guy. I'm gonna do that, but let's first do B. Okay, I want to do both A and B. So let's take B. This is for matrix B. B equals to 3, 2, 5, 6, like that. So we are going to take det lambda I minus b and get this guy here. 3 minus 2 minus 5 lambda minus 6. Again, why not stop the video, calculate the eigenvalues, calculate the eigenvectors, put those into columns of P and do the multiplication. It's exactly the same question. So and then you can see that your idea of what computations to do will be good. Okay, so here we go. I'm going to do that here, minus 10. Then I get lambda squared minus 9 lambda plus 18 minus 10. That gives me lambda squared minus 9 lambda plus 8. I factor lambda minus 8 and lambda minus 1. So I have two eigenvalues, the two distinct eigenvalues. So I know that matrix B is diagonalizable, and I get lambda 1 is 8 and lambda 2 is 1. I calculate the eigenvectors. So let's go for let's do the first one, 1, and I'm looking here and I'm thinking, okay, lambda is now 1. So I'm going to say sorry, lambda 1 is I'm actually doing this one first. Lambda 1, which is equal to 8. Lambda 1 is 8. So I'm going 8 minus 3 is 5. I'm thinking here 8 minus 9, I've got the minus 2 minus 5, and then 8 minus 6 is 2. So there is the matrix there. And if I want to, I can put these things here to show what I'm doing. I am row reducing to find out which values give me 0. I get here 1 minus 2/5, 0, 0. And I get the corresponding eigenvector is 2/5, 1. I go through the same procedure with lambda 2 is equal to 1. And I get here minus 2, minus 2, minus 5, minus 5. And I'm going to row reduce that. You see, after a while, so I get lazy. I mean, these things are not doing row operations when everything is 0 in that column, doesn't get anything. So I tend to omit them after a while. Row reduce, I get this here, like that. And I see that the second eigenvector is this. Okay, that allows me to form the matrix P. P is the matrix. First column is that first eigenvector that I computed. The second column is my second eigenvector. I invert the matrix. Practice. I can't just practice. You can also, of course, use MATLAB, but you want to make sure you can do it by hand. So I invert the matrix. I get this guy here. There he is. Okay, and then I can check p to the minus 1 AP. Let's multiply that out. I take p to the minus 1. B. See this right? I'm doing B, not A. B. And B is 3, 2, 5, 6. And then p to the minus 1, b, and then times p, 2/5 minus 1, 1, 1. I do that product, practice if you need to, and I get this guy here, 8, 0, 0, 1. It's a diagonal matrix, and the eigenvalues are right there on the diagonal. We have one final example. We're going to do a 3x3 example. That was this guy here. I think I called him A again. Here he is. It was this one, 0, 1, 0, 1, 0, 1, 1, 1, 1. Okay. I'm not going to write down all the arithmetic steps. So we do exactly the same thing in the 3x3 case. We take a look at det lambda I minus A, and that is going to be the determinant of lambda minus 1, 0, minus 1, lambda minus 1, minus 1, minus 1, lambda minus 1. again, good idea just to stop the video and have an investigation of this yourself. I'm calculating the eigenvalues. Okay, I'm going to expand along the first row, cofactor expansion. Okay, that's a -1, but then we know that that position has a -1 in the cofactor expansion. So it looks like this. Done. And then, so now I have two 2x2 determinants to do. Let me get this here. There's lambda -1, -1, and minus lambda -1, -1. Okay, I combine this all together and I get a cubic that looks like this: lambda cubed minus lambda squared minus 2 lambda, which I can factor as lambda times lambda squared minus lambda minus 2, and that is lambda minus 2 and lambda plus 1. I have 3 distinct eigenvalues. So I get lambda 1 is 0, lambda 2 is 2, and lambda 3 is -1. 3 distinct eigenvalues. This is a diagonalizable matrix. Each eigenvalue has algebraic multiplicity 1. You can confirm if you wanted that each one has geometric. In fact, we're going to do that by calculating the eigenvector. We're going to see that the geometric multiplicity of each one of these is also 1. So finding the eigenvalue, the eigenvector for eigenvalue this 0, we're going to take this guy here. I'm going to omit the last column of zeros on this one. I am solving x equals 0 here. I'm just not writing that column of zeros anymore. Okay, I row reduce. If you need practice row reducing, go ahead and do that, or potentially use MATLAB if you're confident about your row reducing. Get this here. This tells me that V1 is this eigenvector here. Okay, there's 2 leading variables, and then this one is free, and the other 2 are here. Okay. Right. I do the same thing for the second eigenvalue, which is 2. I'm going to solve this AX equals 0. I'm going to just write this matrix out for you. And I row reduce, and I get this here. -1/3, 0, 1, -2/3. There's a lot of computations. MATLAB to the rescue, as long as you know what you're doing, right? As soon as you know what you're doing, you stop making the calculations yourself and let MATLAB do the work. Just do enough so that you can do it by hand if you need to. Okay, so I get the second eigenvector. I get the eigenvector corresponding to the second eigenvalue. I go ahead for the third one. It's this guy here. Lots of calculations here. I will reduce. Right, 2 leading variables. The second variable is free, and then the other ones are like this. And that now allows me to form the matrix P. I form the matrix P. I put the eigenvectors in as columns. I invert. If you think you need practice inverting, go ahead and invert one time in your life. Invert the 3x3 matrix by hand, yeah, by augmenting with the I3 and doing full Gaussian elimination to the row reduced echelon form. You will get this. Oh, I got this here. Okay, now we can compute P -1 AP. but actually in some ways that's going to be D. We know it's going to be a diagonal matrix if we haven't made a mistake. So we definitely should check, right? Meanwhile, though, I can write what out this die is going to be. It's going to be 0, 0, 0, 0, 2, 0. I know it's diagonal, 0, 0, minus 1. And I have entries on the diagonal, and what is on the diagonal are those 3 eigenvalues, and this one is here. The corresponding eigenvectors are like this. Okay, so there's my diagonal matrix. I now have found a matrix D, which is diagonal and similar to A. That is the diagonalization procedure. First step, can you diagonalize? When the answer is yes, find the eigenvectors, and that gives you the matrix that you need to diagonalize. And that's all for this lecture. Thanks very much, guys. See you next time.